Hi and welcome. In this video I'll be talking about threaded bolt and nut joints, and I think it's worth explaining those, even though it is something that we've always seen, it's always been around us, so it goes without thinking much, but they have some interesting things about them and I think they are worth explaining. So I have already made videos explaining what torque is and explaining mounting pastes. So if I don't forget, I'll make those pop up in your top right hand corner so you can click on them and see. Even though I will try to make this video cover all the important aspects, so you don't really have to watch any other videos. And so let us begin. This is what I'm talking about. Here I have a bolt and a nut on the end of it and some parts in between and some washers. Okay. And I draw like a 3-year-old, but that is what I try to draw here. Here we have one bolt that has relatively coarse threads, so they go at a greater angle, covering more distance along each turn, along one thread, while this other bolt has more threads that are more tightly packed and cover smaller distances, and they are generally smaller. So that is thread coarseness or thread pitch, how it is called. It is expressed in threads per 1 inch, like here. That would be counting how many threads there are along 1 inch length. So that is one way to express thread pitch, and another one is to express the distance between two threads in millimeters. So there are two ways of expressing how fine or coarse a thread is. So here, this is what thread pitch looks like. And I hope you can see that there are threads one next to each other, and the distance between the tops of two adjacent threads is what I drew here. And this is an extreme example. This is like splines, so there is nothing going in circles here. This would require for us to have a splined, not to just slide onto it. And one of the reasons to use threads, I will explain that, but here another thing that I want to note, just to keep in mind, we'll come to that later, is that if we magnify our bolt or nut or threads, like I try to draw here, you can see that surface is not perfectly smooth, it is a bit jagged. For all important purposes, when we talk about the loads and the friction, we can assume that the surface is not perfectly smooth, and it does provide some resistance. We'll get back to that later, but for now it's important to understand it. And now let's get back to our nuts and bolts. Why do we create thread anyway? Well, in the first place, it is because we want to get something fixed and stuck in place, mounted using nuts and bolts. I'll explain how they do that exactly and why that is such a brilliant idea that is very often used. And in order to create enough preload to keep them in place, and for some other reasons that I'll explain, we have these threads that go in circles. So when we take a nut, here it is, when we take a nut, we need to turn it in circles in order to screw it on. If this thread pitch is coarser, so there are fewer threads per 1 inch or the distance is greater, that means that for one turn our nut here would cover this distance here. On a finer pitch, one whole turn of the nut will make it make a shorter distance, cover a shorter distance. And in some way that is like using lower gears on your bicycle, the easier gears, or lower gears on your car or motorcycle. So with a certain number of turns you move more slowly, but you do it more easily if there is some load or something. And when we are tightening something, we are in fact creating preload. and working against some load. So that is the first thing to understand. So finer thread allows us to use the smaller torque for tightening to get the same amount of preload as we would get with a coarse thread, with the less fine thread. And why is that preload important? Well, a way to visualize nuts and bolts and all these other things is as if they are made of rubber. Because even though you cannot visibly and noticeably see any elastic deformation, so stretching or compressing, they do happen and they do make a difference that is measurable and noticeable. If we use spokes as an example for bicycle wheels, when you calculate the optimal spoke lengths for thinner spokes, you can calculate 1 millimeter or more shorter spokes because they will elongate more as you tighten them to the same tension as you would tighten any thicker spokes. So the metals do elongate, even hardened steel. And here we have a drawing of this. So I take these two parts, and if I want to keep them snugly together or hold something between these, like this is for the seat post, I would use a nut and a bolt and tighten them. If you don't tighten, if you don't create preload, it is as if you have some clearance practically, because when load is applied and when these things elongate, you will have them moving and unscrewing or loosening completely. Before we get to this, let's just discuss what prevents our nuts and bolts from unscrewing. Well, this friction that I talked about is one of the things that prevents them from loosening, along with the preload. Because as we are tightening bolts or nuts and creating some load, it also increases friction as the pressure increases, because we have both the friction of the threads and the friction of the face of our nuts and bolts, so this section that goes against. So we have that face having friction against the surface, whatever it is that we are tightening. So those two frictions, if we create enough preload, will increase as we tighten, and then once they reach a point where that friction is greater than any vibrations or anything else that tends to get our nuts to move and loosen, we have a pretty good connection. So let's move on. Here, if we tighten, take this bolt and the nut and tighten our two parts together, what will happen is that the bolt itself, because it's usually much thinner and more elastic than the things that it tends to keep together to mount, our nut will elongate. So this section between the ends will be a bit elongated. It will stretch a bit. While these are things that we are trying to keep together will compress a little bit. And so we have a bolt elongating and the things we need to keep together compressing. Once we compress them, no matter how much, it is usually very small in micro nanometers or something, but they do compress, they will exert force against our nut and our bolt's head and also against each other. And now what happens when we try to pull them apart by using some force? So for example, if we have this like a saddle holder, if saddle rails go through here, and as we rock our saddle, and it tends to pull these apart, so we have some force trying to pull it apart. What happens with our nut? It also gets loaded by a certain amount of force trying to even further spread it out. Okay, and because it is more elastic generally, it will elongate a bit more than these two things that it holds together will deform or elongate. However, the force that these things that we keep together are pressing against each other and in reaction pressing against the nut and the bolt will slightly decrease as soon as our nut elongates, or sorry, bolt elongates by even a fraction, because these are very stiff. So 1 micrometer of the bolt's elongation will cause these to lose a huge amount of tension, of compression, because they are much stiffer. So it's like having a spring that is very thick. So if we try to press that spring by 1 millimeter, it's difficult. If it's a very strong, very powerful spring. And the same thing happens when it is pressed. If we release it for just 1 millimeter, there's a huge amount of force being reduced and released. Of course, the example is not perfect, because if springs are with a linear compression, it might not go exactly that way, but this is the principle here. So as soon as we make a smallest amount of bolts elongation, the pressure that we have here, the forces, will diminish greatly. And what that means, I will try to draw it here. So if we have this amount of force being applied to our system, roughly this equivalent of force will be taken up by the loss in compression of the parts, and only small amount of force will be put as extra load on our bolt and nut. The greater the preload, the more this is in favor of not putting any extra stress on our bolt. And so, apart from preventing the parts from unscrewing, loosening, and another reason why proper preload is important is because it prevents the bolt from having huge difference in loads and huge cycles, and thus breaking from fatigue. So those are 2 reasons why it's important to have an appropriate preload. Okay, so how do we measure that preload, and how do we know when it is enough? Manufacturers, when they build parts and assemblies, usually do all the calculations based on how coarse the thread pitch is, whichever they opt to use, and they can calculate how much torque you need to put into tightening the bolts and nuts in order to get the optimal preload. Of course, they also take into account how strong the bolts and nuts are. All those have to be aligned. But what we can easily measure, and what we usually work with, is the tightening torque. So we don't measure how much preload we've achieved. It's not very practical to do when we have all things assembled, but we can measure how much torque we are using to tighten it. We can even feel it by hand, how strongly we are pulling, and depending on how long our lever is, we will use more force or less, but we can sense that torque. And that's what we measure, and that is the reason why torque specifications and recommendations exist. I will explain that further a bit in a minute, just to touch up on the thread coarseness. If we have some softer, more sensitive materials, you will usually use bolts with a finer thread, because they are less likely to get unscrewed without having too much preload. This is the opposite example here. No matter how much you press it, how much preload you create, as soon as you release any pressure, the nut will go out, because it has splines, and this is somewhere in between. So here, when you have a coarser thread, you need a lot more preload for that friction to prevent the nut from unscrewing. So those are some things that are taken into consideration. Likewise, if the construction you are building needs a lot of preload for it to function properly for whatever reason, you will usually go with coarser threads, because they are stronger and they can take more You have more room for more material to make them thicker and stronger, so they can take more preload, more force. So those are some things to consider. So more sensitive, softer, smaller appliances and assemblies usually use fine thread pitch, and the ones that need a lot of preload usually use greater diameter, thicker bolts and with a less fine, coarser pitch. And now when we are assembling and we want to measure the torque, because that's what we can measure, because of these imperfections, surface imperfections, it is a very good idea to take some mounting pastes whenever that is possible. Sometimes it's not advised, but generally it usually is. And to smear that mounting paste onto the threads of the bolt and also onto the face of the nut and the bolt, so the part that goes to press against the material, you also want that smeared with mounting paste so that it can smoothly turn without this friction coming in play. Why is that important? Well, if you have a specified torque of say 5 Newton meters and you tighten the nut for 5 Newton meters, if the friction is what stops the nut from tightening, you will not have achieved the desired proper preload, which is important. And the main reason for this long, tedious video. So if you put mounting paste or grease, whatever makes it slide easily, then you will take the friction, that jaggedness and those things out of the equation, and you will have a nice, smooth, even tightening torque to assure that you have the proper preload. But there is a catch. When manufacturers specify tightening torques, sometimes they specify 4 lubricated connections, joints, so that you know that torque is specified for using it, for applying it with applied mounting paste or grease if you don't have any mounting paste, or oil, whatever. However, sometimes the torque is specified for dry fit, and unless that part is recommended to not be used with any mounting paste for whatever reason, then it is, in my opinion, better to use mounting paste but decrease the recommended torque by 20%. So for 5 Newton meters, if it says dry fit recommended torque, you should use 4 Newton meters, so 20% lower torque, and you're good. Because of that jaggedness, if you go and actually tighten it with a dry fit, you might end up with not having enough preload. The catchy part, the tricky part is the cycling industry, where very few manufacturers note that explicitly. So you have to guess. So I buy some parts and see, is there a bit of residue of some oily or greasy stuff on parts? Okay, maybe then they mean that torque should be applied with some mounting paste or grease. Maybe that's taken into the equation. Or if they are completely dry, I'm never sure. I'm never certain. What I do when I have some specified torque, if it is a range, like say 12 to 14 Newton meters for crankset pinch bolts for Holotech 2 cranks, for those I go with a bit reduced torque, so the lower limit, but I use mounting paste. So that's one of the ways, and it's worked for me so far. For other assemblies, when it is not clear and they have just a set value, so for example for most stems, and if you mount the bolts that mount to hold the handlebars in place are set to 5 Newton meters torque, or 4 or 6 sometimes if there are only 2, something like that. For those, if I'm not certain, I try not to overdo it, because if I overdo it, I will create more preload and might damage the threads, so that's not something I want to do. I go with about 10% lower tension and I use mounting paste. So it is a bit of a guesswork, but that's what's worked fine for me so far, except for carbon fiber parts. There I err on the side of caution because those things are easily squashed if you put too much preload, so carbon fiber handlebars or whatever. When I work with those, if I'm not sure if the specified torque is intended for a dry fit or for a lubricated fit, I use mounting paste when possible on the bolts and nuts, but I go with a 20% lower torque and see if it is held in place firmly, give it a test ride, check it out on the stand, and it usually works okay. I also use mounting paste for carbon fiber on those contact areas, but that's topic for a separate video. I have an article on that, mounting pastes for different materials. I make that pop up with the magic of video editing. So I think I have covered everything. I hope if you have any questions or comments, let me know. And thank you very much for watching, and cheers.